In lesson 5 of chapter 9, labor market discrimination, we're going to continue what we did in lesson 4. In lesson 4, we tested the hypothesis that the difference in male and female average salaries was 0. An equivalent version of that test is the coefficient of a simple regression with the slope coefficient for the female variable being 0. And we rejected that with simple regression. We're going to re-examine this question by estimating a multiple regression. So we're going to retest that hypothesis using multiple regression. And we're going to use multiple regression because more variables are included. And generally, the more evidence you gather, the better decision you can make. So things other than female might explain differences in salary, right? In my regression that you see down here, I'm going to create 2 new columns in my data set called female X years 1. And what that is I'm going to multiply the female variable by years 1. I'm also going to multiply the female variable by BSBA. And these are called dummy variable interactions. My multiple regression is going to include some college, BSBA, which is college degree, some graduate school, a graduate degree, female, years at the bank. That was years at the bank, right? Let's go back and double check. Years 1 is service, years of experience with the bank, right? And then these 2 interaction terms. Now, your interaction terms might be different than mine. Okay, so here's the data set. The first thing I want to do is I want to move salary from the column I, and I want to put it in column B. Because this is our Y variable, and in Excel, the variables on the right-hand side need to be side by side. Okay, the next thing I want to do is I want to order them the way we see them here. So some college, I'm going to copy this and paste it to the right of salary. Then I'm going to get BSBA. I'm going to put it to the right of some college, right? Some college, BSBA. And then I'm going to get some grad school. I'm going to put that to the right of BSBA. And then grad degree. And then female. Okay, then I need years 1. And then I need 2 new columns, right? Female years 1 and female BSBA. So insert. Let me auto widen those columns. Okay, so I'm going to copy this here. The X means multiply, right? I'm going to replace this name with, copy. I'm going to auto wide. I'm going to grab this one here and put it here. Okay, so the next thing I have to do is I have to take and multiply the observation under female times the observation under years 1. Okay, now when I hit enter, it's going to automatically fill in this column. That's the cool thing about Excel and formatting your data in a table, right? So all the way down here, you can see what it's doing. It's multiplying the 0 times the 3, right? So the only time we get anything in this column is when we get down here to the female, right? Down here, all of a sudden it goes from 0s to 14 because we're multiplying these 2 things here, right? So everything below is identical to this and below, right? All right, so now we got to do the same thing for female and BSBA. So we're going to take and multiply the female observation times college degree. And again, we're going to get a bunch of zeros, right? We're going to get a bunch of zeros because I ordered them by female here, right? I ordered them by female. I have the males on top and the females on the bottom. So all these are zero until we get down to where we're having females, right? So there's our first female in the data set. And we're multiplying this right here by BSBA. And for this female doesn't have a bachelor's degree, right? This female has a bachelor's degree, and that's why this is 1. Okay. So we have our variables made. I'm going to hide the things that we're not using. Hide. Hide. Hide and hide. And I'll hide this over here too. So that's my Y, and this is my set of X's, right? And they're in the order in which you see them here, right? Okay, so I'm going to click on data, data analysis, regression. I'll hit OK. I need to load the Y variable, right? The Y variable is B, right? This column B, all the way into the bottom or last number, right? So that's your Y variable, salary, right? And then I need to load the X range. And the X range is from C1 down to J209, right? So we got C1 down to J209. I'll go ahead and put the output range in a new document, a new worksheet. We have labels checked, and I think we're good to go. So here's our multiple regression output. I don't need the confidence or the prediction intervals or confidence intervals. I don't need that. What I am going to do is I'm going to use 3 decimal places. I'm going to highlight all these decimal values and format them so they are in 3 decimal places. Okay, and then the last thing I'm going to do is I'm going to auto fit these columns. Now my R square is 0.732. Notice it is higher than what it was, right? Previously, the R score was only 0.120. With more information that that's relevant, we have a R square of 0.732. Now, when we're interpreting the R square in multiple regression, we don't want to interpret the R square. We want to interpret the adjusted R square, right? And notice these 2 values are pretty close. And notice the F statistic is pretty large too, with a small p-value, right? We have this p-value of the F statistic. That's small. This is big. These 2 things are pretty close to each other. And that's kind of what you want for multiple regression. And the reason why that is because you can get a high R square by including a bunch of things that don't matter. So you can inflate this by just adding a bunch of variables. So the adjusted R square accounts for that. And because these are so close and that is so large, we must have quite a few significant variables here, right? That's significant, that's significant, that's significant. These are all very highly significant right here. All these are very highly significant. Some college and female interacted with BSBA is insignificant, right? But pretty much everything else is significant, right? So that's why our R square and our adjusted R square are so close to each other and why the F is so big, right? So the F statistic, p-value into here, 3 decimal places. Then I got my intercept. The intercept is what the salary would be for all these values being 0. So some college would be 0, BSBA would be 0, some graduate school would be 0, graduate degree would be 0, female would be 0, years at the current employer would be 0, this interaction would be 0, and this would be 0. So if all these values were 0, right? So if a person had no college at all, then this would be 0, that would be 0, that'd be 0, and that'd be 0. If the person was male, this would be 0. If the person was brand new at the company, this would be 0. And these two things would be 0, right? So for that kind of person, that person is going to expect to make $24,321.64, right? Now we have some college. I'm going to start from the bottom. It's easier to copy these in from the bottom. Here's the interaction. Here's the coefficient for that interaction. The coefficient for that interaction. The coefficient of years at the current bank. The coefficient for female. The coefficient for grad degree. The coefficient for some grad school. And the coefficient for a bachelor's degree, either BA or BS, right? We'll hit enter there. Okay, so now we got to get our p-values. The intercept is significantly different than 0. Some college coefficient is insignificant. College degree is significant. Some grad school is significant. Grad degree is significant. The female variable is significant. Years at the bank is significant, right? 0.000. The next one is 0.000. And then finally, we have the last p-value, which suggests that this last intersection or interaction, the interaction of female and BSBA is insignificant, right? Okay, those are our results. For the following round, 2 decimal places and test all hypotheses at the 5% level, right? So the first thing we want to do is we want to interpret the adjusted R-square, right? The adjusted R-square. We want to convert it to a percentage, right? So we got to move the decimal place 2 spots. And it says use 2 decimal places. So let's go up here and add a decimal place. So 72.11%. The salary varies from individual to individual working at this bank, right? So 72% of the variation in salary is explained by this model here, right? It's explained by this set of variables in a linear multiple regression, right? So that's a lot better than what we had in the previous lesson, right? In the previous lesson, only 12% of the variation in salary was explained by the model, which included just the female dummy variable, right? So that should give us a warm, fuzzy feeling, right? The p-value, the F statistic says what? The p-value is really close to 0. The F statistic is huge. And the F statistic is testing whether this coefficient and 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 this coefficient are all equal to 0 at the same time. So this is a collective test. Are these differences between these values and 0 significant or insignificant? Well, the F statistic is way out there in the upper tail of the F distribution. It has a p-value close to 0, right? And if we use a 5% level of significance, this F statistic would be way above the critical value. So we're going to say that the model is significant, right? And that's pretty obvious from the p-values here, right? So this is smaller than 5%, so that's significant. That's smaller than 5%, so that's significant. Each one of these is smaller than 5%, right? So this, and that are significantly different than 0. So it makes sense that we would conclude that our model is significant, right? Now, how many of the variables or predictors are significant. We have 1, 2, 3, 4, 5, 6. We have 6. The intercept is not a predictor, right? We have 6 that are significant. Having a bachelor's degree increases a bank employee's salary by what? So having a bachelor's degree increases the bank salary by that amount, right? So if you have a bachelor's degree, a BA or BS, you're going to earn $4,500 more than people that don't have a bachelor's degree, right? Taking some graduate school courses increases a bank employee's salary by what? Almost $6,000, right? Almost $6,000. Having a graduate degree really increases your salary, right? It increases it by almost $10,000, right? That should be a 3 because around the 8 makes the 12, 13, right? The female coefficient implies that the average salary of female bank employees is $5,394.80 more than the average male bank employee. Well, that's kind of interesting. If we go back to the simple regression, this coefficient was negative. So in this model, females are making less than males. But in the multiple regression model, where 72% of the variation of salary is explained by this set of variables, we actually find evidence that females are actually making more money than males at this bank, which is really surprising because this is back in the 1980s. This data set was, I think, collected in the 1980s, right? So that's really surprising there. If we use simple regression, we have evidence in support of discrimination. Females are making less than males. But when we account for differences amongst individuals, college matters, years at the bank matter. When we account for other information in the model, the discrimination goes away. So each additional year of experience at the bank increases the average sale of males by what? This right here is the salary equation, just part of it, right? I have the coefficient for female times female. So the coefficient of female times female. I have the coefficient for years 1 times years 1, right? Then I'm subtracting off the coefficient on the interaction of female and years 1, right? And then yada, yada, yada. So I'm kind of ignoring the stuff to the right and the stuff to the left, right? So what I'm going to do is I'm going to copy this twice. I'm going to paste it down here. I'm going to do 1 where female equals, I'm going to do this for the female equation. So this will be 1, right? And this will be 1. For male, this will be 0. This will be 0. And this will be 0, right? Because remember, female is a dummy variable. Okay. So now I'm going to simplify this value. This product here is 0, right? 0 times this times that is 0. So this part's gone, right? This part's gone here. Okay. And this part's gone. Okay. Now, if I differentiate this with respect to, years 1, if I differentiate this with respect to years 1, right? This right here is gone in the derivative, right? And everything else is gone too. So all I have is this coefficient here. If I do the same thing up here, if I differentiate this with respect to years 1, this part is gone. This is gone. Years 1 times 1 is years 1, right? And then this is gone. Okay. Everything to the right is gone. and everything to the left is gone, right? So for female, right, an additional year of experience at the bank is this coefficient minus that coefficient, right? And I'll do that in Excel. I can just highlight these two, and the sum is 426.15. 426.15. Make that a 5. Okay, the percent decrease from R square to adjusted R square equals what? So the percent change equals what it is minus what it was divided by what it was. And we're going to multiply that by 100, right? And then we'll reduce the number of decimal places to 1 decimal place. Okay, so the percent decrease from R square to adjusted R square is 1.5%. For practitioners of multiple regression, a large adjusted R square and a large F statistic and a small difference in R and adjusted R square are desired regression properties. The coefficient for female went from a big negative number to a fairly large positive number, right? So this kind of torpedoes the claim of discrimination at this bank, right? However, when you look at each additional year of experience at the bank, men are paid an additional $1,500 for each additional year, where females are only paid an additional $426, right? Now, if we're talking about the average male and the average female, find the break-even point, right? So we have year 0, year 1, year 2, year 3, year 4, year 5, year 6. I'm going to put this the male column and this the female column. Each additional year for males is 1463.62. For females, each additional year of experience at the bank increases their salary by that amount. But females start with a bigger differential, right? So $5,394.80. So let's find out where the overtaking year is. Okay, so the females, they start out making that. I'm going to F4 it. Plus that for each additional year. So I'm going to multiply that coefficient by 0. I'm going to F4 the C1 there. Okay, and then I'll pull this down, right? And then for males, I'm going to F4 that value and multiply it by the year, right? And we'll find out where the males overtake the females. Okay, so it looks like at year 5, the differential between males and females is disappearing. So females are making more than males through the first 5 years of service, but in year 6, the males start making more money than the females.